Good morning, everyone. In the words of the inimitable John Cleese of Monty Python, and now for something completely different. So the holographic properties of water. Before I begin, I'd just like to say a big thank you to Vladimir Voykov and to Rupert Sheldrake, who both proposed me. And of course, very big thank you to Gerald Pollack for sending me a kind invitation. So let me begin by just explaining a little bit about the Cymoscope instrument that I developed and over a number of years, just so you get a feel for how it functions and what these various aspects are. So I think you can see quite clearly in the center here that we have what looks like a Petri dish. It's actually, it is a kind of Petri dish, but really what this is, it's made of fused quartz, and the bottom part of it is, the actual bottom, is black quartz, and the whole thing is precision engineered. So it's a little bit of a kind of upscale Petri dish, you could say. And from the center axis of that small, what we call the visualizing cell, from the center axis is a piston. That piston goes down to a voice coil motor. And then obviously we put some form of liquid in the visualizing cell in order to make sound visible. So the essential aspect of this instrument is that it makes sound visible. It does so by imprinting the sonic periodicities onto the surface and subsurface of water, thereby essentially making them visible. What you've really done is you've transcribed the sonic periodicities into water wavelet periodicities. Now, the parts that you can't see, of course, as I mentioned, we've got the voice coil motor that you can't see, but then there's a whole chain of audio equipment that drives that voice coil motor. In the example that I'm going to give today, we start off with a very standard audio oscillator, but this is an analog oscillator, not a digital oscillator. And it has an accuracy of 0.001% total harmonic distortion. So when you get a sine wave out of this oscillator, it's extremely pure. From there, we go through a series of other signal processing techniques. We have, for example, a compressor limiter, which just controls the dynamics of the signal. We also have, obviously, an amplifier. But the other key component that we have in the signal path is a 30-band Clark-Technic graphic equalizer. And the purpose of the graphic equalizer is this. You might already have imagined that mechanical or electromechanical system comprising the visualizing cell, the piston, the voice coil motor, and so on, all of those components combined have a series of natural resonances. First of all, we identify those resonances, and it's a simple process. You use in this case, we used a B&K accelerometer system. It's a tiny, tiny little, one of the world's smallest accelerometers, so it has hardly any mass. You apply that into the center of the visualizing cell, and then you run a sweep, a frequency sweep, through the bandwidth that the cell is going to be used for. And then, of course, what you see on the resulting frequency sweep is a number of peaks and troughs. So the peaks are obviously the resonance peaks of that particular electromechanical system. And then in order to neutralize or effectively neutralize those peaks, we then use the 30-band Clark-Technic equalizer. And what we do is simply dial in a kind of inverse profile so that it gives you a virtually flat frequency response, so that you know whatever signal you put into the cymoscope, you should get an analog, a model, if you like, of that frequency made visible. It can be a single frequency, or it can be a complex frequency like music or voice. Whatever you put in, you should get a fairly accurate analog in the form of a pattern, rather than in the form of a spectrum analyzer that we've come to know and love, for a long, long time. So this is a completely new type of instrument. I've built a number of them for scientists around the world, and so it's not that I'm not looking for business here. This is basically a tool. We just basically want to see this out in the world because we really do believe that it has a huge potential in terms of a scientific instrument. So, going on from there, this item that you see in the corner here, this is a Peltier control module. So Peltier, you probably know, is the system where you can control temperature just by putting a current in, and if you reverse the current in one direction, you will get the Peltier system will heat, and if you reverse it in the other direction, the Peltier system will cool. And it's very important to have the correct water temperature for whatever the experiment is that you're doing. In the visualizing cell, I've tried a lot of different fluids. One of the fluids I tried was Scotch whiskey. And while it definitely did not image as well as pure water, which is that we normally use, the medical grade water, it has one advantage, which is, of course, at the end of the experiment, you can just drink it. But anyway, we have found that that pure water is really the very, very best at providing beautiful imagery. So I think that's the essence of the instrument. I don't want to belabor it because we've got a lot of material to cover here. But I do want to mention a few of my scientific heroes. There's been quite a lot of talk about scientific heroes at this wonderful conference. And some of mine that relate directly to this work. Then we move forward to one of perhaps my greatest hero, Michael Faraday. And Michael Faraday in 1832 did some experiments he called crispation experiments. And the reason I'm particularly mentioning Faraday was because all those other people were seeing forms in sand or powder or dust or this kind of thing, whereas, in other words, particulate matter, whereas Michael Faraday actually thought, well, I wonder what happens when we use liquids. And so Michael Faraday did he did about 6 months of work on this, and he was seeing beautiful patterns forming on the surface of the liquids. I think the problem was, it was really a long way. He didn't have the electronics, to drive. He didn't have the controls that you really need to do this kind of work. And so after 6 months of work, interestingly about Faraday, he didn't find any applications. And, Faraday was a little bit like me in the sense that I love applications to come from science. And so it was interesting that he didn't find any. But I think it's because he just didn't have the tools at his disposal in that era. Anyway, I put this little note in, as you can see, current hydrodynamic or hydromechanics, as it's sometimes called, theory includes non-linear standing waves, which are nowadays in scientific speak called Faraday waves. But also in the modern vernacular, this is the science of cymatics, or let's say it's an emergent science because it's still coming. I love this quote by Louis de Broglie. The actual state of our knowledge is always provisional, and there must be, beyond what is actually known, immense new regions to discover. Well, we can certainly say that in the case of cymatics, that is absolutely true. I'll just take a drink of water. Moving on from there, this is also related to de Broglie. Cymatic phenomena in which fluid particles act in a wave-like manner can be considered a class of matter waves, sometimes referred to as de Broglie waves, which are a central part of the theory of quantum mechanics, being an example of the wave-particle duality. So if you think of it, every single molecule within that area of water is, essentially the particle, and yet it's moving in a wave-like manner. What excites me about this is simply the fact that here we have a medium, cymatics, Faraday waves, whatever you want to call it, which is actually a potential tool for investigating quantum dynamic theories, quantum dynamic experiments, and so on. So I think it's very exciting. Now look at this absolutely beautiful photo. What you can see is that there's a couple of water drops have been ejected there. This is not my photo, by the way, but nevertheless, it's a beautiful photo. What you can't see is what's going to happen next. You know, what's going to happen when one or more of those droplets of water enter the water. I don't know if you've ever puzzled on this, but I had for a long time. What actually happens when a drop of water like that falls back into the water? Well, we know what we can see with our normal eyes. You throw a pebble in a pond and you get the concentric ripples rushing away, etc. But what's happening in the structure of the water itself, under the water, subsurface? Well, it wasn't until a couple of years ago, about 3 years ago actually it was now, that we did some work with a group of scientists called Merion, the Merion group of scientists. And the result of this work, after about a year's worth of work, so it was published in 2012, I think it was actually, was a 500-page textbook called the Merion Matrix. I highly recommend it to you. It's a superb textbook, and my lovely wife, Annalise, edited a large part of it, put it into language which hopefully is nice and clear. And a large part of this book, the Merion Principle, if you haven't heard of it, concerns a number. It's a 33-digit number. Starts with 797 and goes on many, many digits. The belief is of this group of scientists that it basically encapsulates a creative principle of the universe. So it's a pretty big thought, and the book obviously sets out why that should be, or why that might be so. And the work that I did in contributing to that book, I contributed a chapter on cymatics, but I also did a lot of experiments with this group of scientists, and this was one of them. Now what you see here is a kind of, you could call it a metal petri dish. You probably can't see it on that screen, but if you look at the monitors, you'll see it a little bit better because it's not terribly bright. But you see a water droplet that's being ejected from the water. This is running at 7.97 hertz again. Sorry, I mentioned that long number. The first 3 digits we used, 7.97 in terms of hertz. And this is a pure sinusoidal tone going into this with that cymoscope instrument that you saw earlier. So what happens when that water droplet re-enters the water is that it's a percussive action, of course. So it enters the water with some force, and it creates a pressure wave in the water. And the result is a torus, as you can see, a toroidal feature, which you might have expected, thinking, well, okay, you've got a percussive drop of water hitting the surface of the water, going slightly under the surface and creating a pressure wave. So you could think that that is the case, and there is some validity to that thought, of course. But then you would think, well, I know what happens next. That torus shape is going to rapidly expand away from the site of this percussion. But in fact, it doesn't. I could have put the video in, but for lack of time, we haven't done that. But if you actually look at the video of this is just one frame from the video, you will see that that torus actually sits there quite nicely during, as long as you leave that 7.97 hertz going in, there's the torus standing before you. Now, admittedly, in this case, the drop of water is going plop, 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 it's coming in and out of the water. So, you know, you've got a mechanism there where you can kind of think, yes, we know why that torus is there. But in fact, there is something else at work here. If you were to put that drop into open water, of course, when you did that, there would be a torus under the water, theoretically, and it would expand away, just like we think. But when you do it in this sense, when you have a boundary condition, that torus just sits there, because, of course, there are opposing forces coming in continually from that boundary condition. In other words, what we're doing here, through that percussion in this case, is structuring the water. And what we're actually doing is we are creating compression areas in the water that have a different refractive index to the normal body of water around it. And therefore, if we have a light source above, I should have pointed that out on that earlier photograph of the cymoscope, we have a circular light ring sending light down on axis into the water. If you have that situation, then the light will obviously reflect off that different refractive index and allow you to see that with your naked eye or photograph it with a camera, which is obviously what we've done here. I should also mention that the camera in this case is pointing at a roughly 45-degree angle, and it's focused under the water, not on the surface, you see. So that's why we're able to, that's why we can see that torus, because we're literally focusing under the water. So going on from there, what about this? Isn't that a beautiful image? What this is, as you see, it's 3D holographic-like cymaglyph created at 22.2 hertz by sonically compressed regions of water that have a different refractive index to the surrounding water. Now, there's a lot of information that can be gained from this image. This is not something that's been made in Photoshop. You know, this is an actual sound image in the water. You can't see the boundary condition because it was removed. That part was removed photographically, but there's been no retouching absolutely of that image. That is a real image of sound in water. Because it's a 22.2 hertz frequency, and because it's coming from an analog oscillator that has this very, very low distortion, we can draw certain conclusions. Let's imagine, if you will, that we can zoom in on one water molecule in any part of that beautiful, what we call a cymaglyph, you know, the word that we've created to say effectively sound image. If we could zoom in on any one molecule, what you would have to find is that that molecule is vibrating at 22.2 hertz, obviously. And if you went anywhere else on that image and they zoomed in, you would find the same thing. Well, what does that mean? And yet we've got all this structure, this beautiful structure, you see? So this is why I think it's quite safe and conservative to say that it's holographic-like, or that we could use the word perhaps quasi-holographic, but certainly there are holographic properties to this. But another very important aspect to this is if we can create these kind of beautiful patterns in water simply by injecting a frequency or frequencies into the water, then there are huge implications for medical science, if you think about this. So it means that all of the sounds around us, whether it be people talking or music, if you imagine classical music, what that's doing in your body, this kind of image could be appearing in the visceral waters of your body, where you've got boundaries, certainly. Wherever you've got a boundary, you're going to have images that can form. Now, one of the areas in your body that you absolutely know you've got nice, clean boundaries are the membranes of cells. And in fact, I have done some early work, microscopy work, with living cells where you can literally see the pattern on the surface of the cell. So just thinking ahead a little bit about the possibilities for sound therapy as a mechanism, that we're looking into a mechanism, why does sound heal? We know it does. Ultrasound is used every day in hospitals as an actual therapy, not just, you know, for diagnostic tool, but as a therapy. And yet no one knows in the medical community why that ultrasound heals. And there's a whole group of people, including my dear friend and colleague Gary Buchanan, who's speaking next, who uses sound therapy on a daily basis. And I'm sure he'll give you some more insights into this. But I think you can see that if we can create beauty in the body of the water, not just on the surface, then there's a big implication here for many aspects of science. The holographic principle itself, there are many, many definitions. I like this particular one by Zimmerman-Jones. The total information contained in a volume of space corresponds to an equal amount of information contained on the boundary of that space. And here you see a young lady playing a violin, and of course the sound that's coming away from her violin is spherical, because, as I'm sure you know, all sounds, all audible sounds at least, are spherical in their space form. And all light, all electromagnetism is spherical in its space form. So when we're talking about sine waves and so on, what we're really talking about is sound bubbles or light bubbles. But of course, the wave particle, the graph, is simply the oscillation, the movement of the bubble in and out that's carrying the actual information, the oscillatory information in somewhere. Anyway, if we could go with a super microscope or something and go, it'd have to be something very special, go down to the surface of that bubble and actually see one of the air particles, whether it be an atom or a molecule of some kind, and actually see its vibrational data, and then we were to go somewhere inside the bubble and do the same thing, we would find the identical data wherever we went inside that bubble, or surface or inside. So from that point of view, sound is very definitely holographic, or has holographic aspects to it. Now, have you ever wondered why the cochlea in your ear, which is only about 30 millimeters long when it's unwound, how it is able to detect very long wavelengths? And I give an example here of the lowest note on a piano, which is 27.5 hertz and has a wavelength of 12.37 meters. How can that little 30 millimeter long cochlea actually detect those very long wavelengths? Well, I'm putting forward a little hypothesis here. It has not been peer-reviewed, so take it as you will. The compression and rarefaction in a single frequency or complex array sound wave, I put that in quotes for obvious reasons now that we talked about the sound bubbles, does not mean that different data is present at different parts of the wave. The frequency data is identical throughout the wave, and only the intensity of the periodicities varies at different points in the wave. So when sound vibrations enter the cochlea, the cilia in the organ of Corti responds to the vibrations of individual molecules. Each molecule carries all of that vibrational data. Therefore, sonic frequencies imparted to atomic and molecular particles may be considered as quasi-holographic in nature. At least that's my proposal, that's my opinion. And it would be, one day I will publish a paper on this, and hopefully I'll get it peer-reviewed. Maybe some people will agree with me, I don't know. But it's an interesting thought as to why the cochlea is able to do this. And I did a lot of research online and in other places to try to find an answer to that question when I posed it, and I could find nothing that gave an explanation. Moving quickly on from there, how is the cymoscope able to describe long wavelength sounds onto a small water membrane? That question might have occurred to you. And here's another potential answer to that. Pure water at 20 degrees has a particular density, of course. Air at sea level has a particular density. Therefore, the transcription of airborne periodicities to water wavelet periodicities undergoes a compression ratio of approximately 829 to 1. And therein lies the potential answer to why this actually works. I need to run a little video now. This is looking at the camera, looking down, straight down on that 50 millimeter area of water in the cymoscope visualizing cell. And what you'll see happen, 27.5 hertz. What you see these rings appearing. I'm gradually increasing the amplitude that's entering that water cell, and the rings appear, and then there's a critical point called the Faraday instability point, and suddenly bursts onto the screen a full expression of that frequency, and then I simply then decrease the amplitude and it goes back down. But moving on from there, here on the right-hand side of the screen, you can see the actual photograph of what you've just seen happening with your own eyes there. And you can see that what's happened, in effect, is that the wavelength, those long wavelengths that we've been talking about there, have been compressed. They've been compressed down, and you can literally do the calculation using that 829 to 1 figure, and it actually works. So I think it almost certainly is correct that what is happening here is those long wavelengths, those sonic periodicities, are being literally compressed down simply because of that differential in the density of air molecules versus water molecules. And if any of you want any of these PowerPoint slides, by the way, please see me later and you can have them. And that way you can study them at your leisure if you wish to. Emerging from this experimental result, a posited first law of cymatics could be expressed as this. A fluid membrane compresses incident sonic periodicities in a ratio governed by the relative densities of the sonic and fluid mediums. Again, of course, not peer-reviewed, so you might want to take it with a pinch of salt. But I have posited a lot of other laws of cymatics as I think of them, and perhaps in a future paper, I will actually put them all forward, and I think it'll be quite an interesting paper. Also, modal patterns on a circular membrane, water membrane I should have put in, can be considered representative of a 2D slice through a 3D sound bubble, because the crests of the waves at the moment before Faraday instability are in phase with the crests of the initiating sound. In other words, what you see in the cymoscope, as I mentioned earlier, are literally models or analogues of the input frequencies. Now, the last part of the talk concerns dolphin holographic echolocation of various objects. We're collaborating with a wonderful guy in Florida called Jack Kasowitz, who works with dolphins on a daily basis. Jack had this idea, I think it was 2011 originally when we first did this work, to task a dolphin to use its echolocation beam on a number of submerged objects. So he had 8 objects in the water. There was the flower pot that you see here, there was a plastic cross, there was a plastic duck, a square, a cube, a ball, and so on, other different objects. He then tasked the dolphin to echolocate on each, and then he had a hydrophone to pick up the reflected signal from those objects. He recorded very high-end audio. I mean, you're talking 150 kilohertz audio equipment, which is really high-end, recorded it, and then he played back the sounds, those same sounds, to the dolphin, and tasked the dolphin to pick out which object relates to which sound. And the dolphin was able to do that with an 86% accuracy, which is quite astonishing. And what it meant was that the dolphin actually was seeing sound in these reflections from the speaker that he'd put into the water. Then he had the brilliant idea of taking these objects and his sound equipment and going to a different dolphin facility, 2 hours away by car, put the objects in the water, speaker in the water, played the sounds to this new dolphin, and the new dolphin was able to also identify the objects with the same high accuracy, or similar high accuracy. Again, kind of proving the point that the dolphin is literally seeing these sound images somehow. Anyway, so then what he did was he knew about my work. He came on the phone to me one day and he said, I wonder what would happen if we put these sound files, these literally wave files, into your cymoscope, John. I said, I haven't got a clue, Jack, but let's try it. So he sent me these files on email, and the first one that we did was literally the flower pot. I put the flower pot sound file into the cymoscope, and I saw the flower pot. And I was absolutely flabbergasted. How could this possibly be? You can even see the hand that's holding the flower pot in the water, you see? So it's an astonishing thing. I mean, we obviously haven't got much time here to go into it in depth. There's a bigger image of that flower pot and the hand. And because we believe that the dolphin has the ability to actually change the angle of its beam, there's a cutoff point where the rest of the arm, if you like, that's holding the hand is not seen. So anyway, that we did that work in 2011 and a lot of other objects besides. I don't think we're going to have time to go into, we haven't got time to go into these. No, okay, we'll just rattle through this. And I was going to show you the difference between imaging an object with light and imaging it with sound. Go this way. There was the cube, the dolphin. There's a cube. You can see the cube image very clearly. I mean, it is astonishing. So you're going to ask me, I'm sure, well, what's the mechanism behind that? And we have got some theories, but we haven't got it fully worked out yet. But we think we have some of the answers. This is the big thing that happened quite recently, a few months ago, that Jack thought had this, again, wonderful idea. Let's put a whole man in the water. And what he wanted to do was to task the dolphin to come up to the man and literally echolocate on his face. He said, John, I think you might find there's a face in this file. Well, we put the file into the cymoscope, and lo and behold, we didn't see a face. What we saw was a whole man. So you can see the man on the left there, and then on the right-hand side, there's a computer-enhanced version of that same image. Again, we were flabbergasted because I really didn't think that would be possible. And I got on the phone to Jack and said, Jack, you said there would be a face. There was no face. There was the whole man. He said, oh, John. Anyway, I'm not going to try and do his accent, but he basically was very excited, as we were. What had happened was, as the dolphin was swimming in towards Jim, submerged Jim, it obviously took a snapshot at that moment as he was approaching the full man, as it were, and therefore we got the full image of Jim. And later, Jack was able to turn that file into a 3D plastic print of Jim under the water. So that was fun. But what this all proves, if I can just quickly conclude, it proves that the dolphin is actually seeing with sound, because clearly the earlier experiments had shown that. And now we're actually seeing, it means that the reflections from these objects, the dolphin echolocation reflections, are carrying data that can literally be turned back into images. The dolphin does it, obviously, and now we are doing it with the Cymoscope, even though we don't understand the mechanism fully yet, but clearly there is a mechanism, and it's exciting, and it's something that we will be exploring in the future. So there was a video there of that thing happening, but we can't show that. So I'll just end now, because we did have some theories about how that might all work. There's a paper being published, a phenomenon discovered while imaging dolphin echolocation sound is in the Journal of Marine Science. If any of you want it, just ask me. And that's it. Thank you very much indeed.
Thank you very much, John, for this wonderful dive into the aqueous medium.